The force against the mass. Mass and force. They are the bread and butter of mechanics. For the mass, this is quite literally the case, since the word originates from the Latin massa, a kneaded dough, a lump which adheres together like dough, from the Proto-Indo-European root mag, to knead, to fashion, to fit. The mass is so central to our understanding of the world that physics usually elevates it to one of the three fundamental dimensions, m, the dimension of mass, behind myriads of colorful units like tons, kilograms, pounds, ounces, and stones. The dimension of mass is joined by L and T. L is the dimension of length, or space, and T is the dimension of time. Space, time, and matter, a trinity as old as physics itself. From this perspective on the world, the force F is a mixture of matter, space, and time. The ingredients of this cocktail must come in specific proportions. For one measure of matter m, one measure of space L, and -2 measures of time t. This is usually written like this. The dimensions of F are m, L, t-2. But where does this recipe come from? What if we mix things differently? Instead of considering just the force, in this video we will wonder about any mechanical quantity Q that can be built from a mixture of matter, space, and time. For one measure of mass, we can imagine different results depending on the values of x and y, the proportions of space and time. If the dimensions of Q can be written in this way, from one measure of mass and x measures of length and y measures of time, then we will say that Q is a mechanical quantity, or a mass-carrying quantity. The mass is of course a mechanical quantity, corresponding to x is equal to 0 and y is equal to 0. No spacetime in this mix. The mass is at the center of the plane of mechanical quantities, and we can use the exponents of the spatial and temporal dimensions, x and y, to place the mechanical quantities on this map. We will use the symbol m to refer to the mass, a mass, any mass. Let us place ticks along the x-axis first, which represents the exponents of the dimension of length. At coordinates x is equal -3 and y equals 0 is the density, which is indeed a mass per unit volume. We will use the symbol ρ. Let's place ticks now along the y-axis, time. Where can we go from now? We found the density in the west, and one way to move away from the mass is to slide down a diagonal. This amounts to multiplying the mass by a length and dividing by a time, that is multiplying a mass by a speed, which gives what's called a momentum, p. And we can continue along this path to x is equal to 2 and y is equal to -2. Multiplying the momentum by a speed, that is the mass by a speed square, which gives the energy, E. The diagonal is a nice path, but you can explore the map any way you want. For instance, you can recall that energy when thought of as work can be understood as the product of a force with a distance. So the force must be just on the left of the energy. And the force indeed has dimension m, L, t-2. What do we have so far? Mass, density, momentum, energy, and force. All are examples of mechanical quantities. Note that they all have integer exponents, x and y. For this we say that they are standard mechanical quantities. Most of the mechanical quantities used in physics actually follow these standards. So instead of allowing all positions x and y, let us restrict our scope for now to integer values of x and y, switching from a continuous plane to a lattice. The lines and columns can be labeled by the values of x and y. With this representation, we can now build a table of the standard mechanical quantities used in science. We've only filled a few spots so far. Let's play a little guessing game and try to uncover more. What's just under energy? With dimensions m, L squared T minus 3. That's an energy over time, and that's called a power, capital P. What's above energy with dimension m L squared T minus 1? Well, an energy multiplied by a time, or a momentum multiplied by a length. It is an action, capital H. What is on the left of the force? This one is known under a lot of different names. Sometimes it's called a tension, or a stiffness, or a surface energy, because it can be understood as an energy divided by an area, that is a length square. We'll use the symbol gamma. Moving further left, what do we have? This one also has a bunch of different names, like elasticity or elastic modulus, pressure, stress. It can be understood as a force per unit area, since it is 2 cells away from the force, or as an energy per unit volume. We will use the symbol sigma. Here's what we got so far, including some of the alternate names. Here is a more complete table. Surprisingly, this table does not seem to have been drawn before, even though it is the perfect cheat sheet for students, and a great guide for teachers and researchers. It is a precious tool that we will use on many occasions on this channel. It is still very much in development, so let us know in the comments if you feel we've missed some quantities from our survey. Check Wikipedia, we might have put the table there by the time you watch this video, and it may be updated already. Right now, this table should feel as esoteric as the periodic table of elements. It's nice, but we need to understand how to use it to really appreciate it. The first and most important thing to understand is that all these mechanical quantities can be understood relatively to one another. We started to see this a little when we talked about mass, momentum, and energy being connected by a speed, or energy, power, and action being connected by time, or energy, force, stiffness, and stress being connected through space. A force is an energy per unit length, a stiffness is an energy per unit area, and a stress is an energy per unit volume. These purely spatial connections between mass-carrying quantities on the same line of the table is what we will investigate first, in the next episode on mechanics.